Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Akmal bin Sapon, and today I will be presenting the final project for MMFB 5053 titled Sustainable Material and Process Selection for an Automotive Inner Door Panel, which is Project 2. For introduction, this project was developed for Johan Ventures Sdn Berhad and aims to replace conventional non-renewable materials used in vehicle interiors with more sustainable and cost-effective alternatives without compromising on safety or performance. Joint Ventures Berhad is currently looking to redesign its inner door panel for passenger vehicles. The existing design primarily use steel and petroleum-based polymers. These materials are functional but present challenges such as weight, environmental impact, and cost volatility. The objective is to shift toward materials that are lighter, recyclable, and still strong enough to meet automotive safety standards. So next is project objective. This project had three core objectives. First is to replace current non-renewable materials with more sustainable materials. Second is to ensure that mechanical properties like stiffness, impact resistance, and durability are maintained or improved. And thirdly, to ensure the surface finish and dimensional tolerance meet interior aesthetic standards. And finally, ensure the new design is cost-effective and manufacturable at scale and improve environmental impact. Next is about product constraints and design requirements. Before proceeding with selection, we translated the product's functional and aesthetic needs into clear engineering and processing requirements. Starting with material design requirements, the density must be low to ensure lightweighting, ideally under 1,500 kg per meter cubic, and tensile strength should exceed 30 megapascal to handle mechanical stress during operation enclosure. The material should have good impact resistance for safety, withstanding deadly slams and minor collisions. It also must exhibit thermal stability above 60 degrees Celsius, as car interiors can get very hot. The recyclability and environmental performance are also key to align with sustainability goals. Now for the process-related constraints, the part shape is a dish sheet, a shallow 3D profile common in car door panels. For mass, must fall within 3 to 10 kg. Dimensional tolerance and surface roughness should both be under 1 millimeter and 1 microns respectively to ensure tight fit and premium finish. The process must be a primary shaping method compatible with thermoplastic producing discrete parts in batch production. These constraints were carefully input into Granta EduPack to screen out such unsuitable materials and process. Next, we go to material selection strategy. The material selection process follows HB's four-step method. Step 1 is translation, which is converting design requirements into engineering property targets such as density, strength, and impact resistance. Step 2 is screening, using Granta EduPack 2022 to eliminate materials that don't meet our constraint. Step 3 is ranking, which is prioritizing materials based on performance indices like strength to weight ratio. And finally, step 4 is documentation, which reviewing real-world feasibility, availability, and manufacturing compatibility. Next, slide 7, which is materials screening result. After applying the screening filters in Granta EduPack, only 3 thermoplastic passes all requirements. These were polyamide, commonly known as nylon PA, polylactide or PLA, and thermoplastic polyurethane or TPU. This figure shows the filtered material chart based on mechanical properties and manufacturing compatibility. Next is material ranking. Here we compare the specific strength of each candidate, that's tensile strength divided by density. Nylon PA stood out with the best specific strength, meaning it provides strong mechanical performance at a lower weight. TPU was more flexible but had low strength, while PLA is biodegradable but brittle and more suited for rigid packaging than structural components. Next is selected material, which is polyamide, was selected as the best candidate material. It is widely used in automotive interiors due to its toughness, fatigue resistance, and surface finish quality. It is recyclable, has good thermal and chemical stability, and is compatible with multiple forming processes. Overall, it provides a balanced solution between performance, weight, cost, and sustainability. For process selection strategy, the screen process included thermoforming, blow molding, compression, and rotational molding. These processes were selected based on shape compatibility with a dish sheet, material compatibility with nylon PA, and the ability to achieve tight tolerance and smooth finishes. So this figure shows the result from Granta IDPAC process screening. All four processes passed the initial filtering stage, and our next step was to evaluate each process more thoroughly using a decision matrix. In process ranking, this table summarizes the scoring of each process based on 6 criteria: material compatibility, shape forming, surface quality, tolerance, volume suitability, and costs. Thermoforming received the highest overall score. It's ideal for forming dish panel quickly and affordably, especially at medium production volumes, while compression molding offered good precision, but its tooling cost and slower cycle time made it less attractive. So the final pairing is polyamide with thermoforming. Nylon PA provides strong, ductile performance with a premium surface finish, while thermoforming allows fast, cost-effective production. This combination is commonly used in door trims, dashboards, and other automotive interior components. So based on typical production economics, we recommend a batch size of approximately 10,000 units. At this scale, tooling investment for thermoforming becomes cost-effective. However, the size can be increased with automation. The estimated material cost per panel is between 18 to 22 ringgit, while processing costs are around 12 to 15 ringgit. This brings the total cost per panel to roughly about 30 to 37 ringgit, which is competitive with current plastic-based door panels. For environmental and longevity consideration, nylon PA offers excellent long-term performance. It is resistant to wear, UV exposure, and chemicals. From an environmental perspective, thermoforming has low emission and energy use compared to injection or compression molding. The use of recyclable thermoplastics also aligns with circular economy principles, reducing landfill waste and raw material consumption. To conclude, this project successfully identified a material process pairing that meets all functional, economic, and environmental requirements for the redesigned automotive inner door panel. Nylon PA combined with thermoforming provides and optimized solution for Johan Ventures Sdn Bhd to moving forward. Thank you for listening.